So the second method of targeting with a cannon is to, instead of changing the muzzle velocity by altering the amount of powder you pack in it, you can tip the angle at which you launch the projectile in order to change its landing location. So, I mean, this poor crocodilian creature, I don't know what it's done to make everybody so angry, but if we wanted to get this thing by tipping, I'm still going to have to work out the components of my muzzle velocity despite not having all of the information. So like we did in the last one, I'm going to have an alpha that goes through my chart, and I'm going to have to find some sort of relationship between alpha and time in these two columns in order to calculate the angle of launch that will actually hit this poor creature. So looking at this little arrangement here, x is adjacent to the alpha, so cos alpha then would be Vx over 75. So the horizontal velocity at the beginning is 75 cos alpha. Vy is opposite of the alpha, so that's sine alpha is Vy over 75. So Vy would be 75 sine alpha. So I can start filling that into my chart. It's going to be really irritating, but what can you do? So 75 cos alpha, 75 sine alpha, 75 cos alpha, 75 sine alpha, 75 cos alpha, 75 sine alpha. Alright, going across my final speeds, filling in the information that I know is true based on projectile motion. These always match here and here. My acceleration is 0 horizontally and negative 9.8 vertically, so I can fill that in. If there's 0 acceleration in the horizontal direction, then the final speed matches the initial speed. At a max height, the vertical speed has come to a rest, so that's 0. At the target, because the thing is symmetrical, whatever the initial speed was, it will be the same size, but headed downwards at the target. The distance, 0, 0, and time is 0 at the beginning. Just going to move this up so I have some more room later. I don't know this. I don't know this. I don't know this. Oh, I do. It's 500 meters away. And I should be back on the ground. I guess actually horizontally this has to be 250, doesn't it? Okay. So looking at the information that I don't have, I don't know the max height, and I don't know how long it takes to get there, and I don't know how long this takes. Oop. Not 0. Pink is really goopy. Question mark. Okay. So, like in the last example, I'm going to try and write an expression for the time using this information. And I'm going to try and write an expression for time using the vertical information. And I'm going to hook them together because the horizontal and the vertical time have to match. So trying to use these numbers and avoiding the 0, because zeros would end up zeroing it at both sides of the equation. VF, VI, distance and time, that would be 2 distance is VF plus VIT. Distance is 500, so 2 times 500 equals 75 cos alpha plus 75 cos alpha t. Now I'm going to write this. A 75 cos alpha and a 75 cos alpha is 2 75 cos alphas. I'm going to write it that way because you notice that a 2 on this side and a 2 on this side divide each other out. Which means to get t by itself, I just have to divide that side by 75 cos alpha. So t is 500 over 75 cos alpha. That's my one expression for time using the horizontal information. Using the vertical information, I'm going to combine VI, VF, A, and T. So VF subtract VI equals AT. V final is negative 75 sine alpha. Subtract 75 sine alpha would be subtract 2 times 75 sine alpha equals negative 9.8 t. So t would be 2. Negative and negative undo each other, so I'm left with 2 times 75 sine alpha over 9.8. Okay. So since this time and this time have to match each other, I can set this expression containing a cos alpha equal to this expression containing a sine alpha. So I'll only have one variable left to work with, and hopefully that will let me solve it. So I'm going to switch to yellow then. 500 over 75 cos alpha equals 2 75 sine alpha over 9.8. So I'm going to do some arranging. I'm going to get everything with an alpha over onto this side and everything else over onto that side. So this will come up, 500 multiplied by 9.8. 75 is down here. We're going to bring this 75 down as well, so it's 75 squared. I'm going to leave this 2 here for a reason that will become clear shortly. And the cos alpha comes out. So if I do all the rearranging, I end up with this line. So take a minute to convince yourself that that's moved correctly. Do you notice that by not actually doing any calculations and just moving the numbers around, I can see that the distance to my target ends up here, the acceleration due to gravity ends up here, the muzzle velocity of the cannon ends up here, and this stuff is just like artifacts from the geometry. So that's kind of neat. You almost have a formula there that you could put in for this type of projectile motion. Now to finish this, I've got a sine alpha and a cos alpha in there, and that's not solvable. You don't have a function that can undo both sine and cos. So you're going to have to pull an algebra trick here, and you're going to have to remember from your advanced functions class, hopefully you've taken it, that this is a trig identity. 2 sine alpha cos alpha is the same as sine twice alpha. So at this point, I'm going to actually evaluate these numbers. So let's see, 500 times 9.8 is 4,900 divided by 75 squared equals 0.871. All right. So I've boiled this down to a trig function, so I'm just going to have to arc sine both sides. So 2 alpha equals sine negative 1 of 0.871. So 2 alpha will equal, let's see, clear arc sine of 0.871. Gives me 60.58 degrees. Or, if you recall cast rule, this thing, that a positive sign ratio gives you an answer in this quadrant and this quadrant. So 60.58 is the one in there. This would be 180. Subtract 60.58 should give you 119.42. Now, normally you discount ones that are bigger than 90, but you notice this isn't alpha. This is twice alpha. So we're not quite finished yet. We have to divide these numbers by 2. So 60.58 cut in half gives me 30.29. And 119.42 cut in half gives me 59.71. Well, that's weird. You've got two angles that will work. So if I were to erase this so that I have some room to draw for you, it's always interesting when algebra spits out two answers. You were expecting to just tip the cannon at a particular angle and fire, but algebra has told you there are two ways to do this. So if I were to draw your field, your target, and your cannon, one of these is a 30-degree angle, so that's approximately like this. The other one is almost 60 degrees, so that's like this. So what the algebra has told you is that there are two solutions. There's the direct shot, the one that is going to put more energy into the horizontal direction than it does vertical. Or you could put more energy into the vertical and have it do the high shot. So if you're trying to hit something with a projectile, you have two choices. If there's nothing in between you, you can use this one, right? This is what a rifle is like. You point the rifle at your target and you pull the trigger and in it goes. The high trajectory would be more of a rocket, right? You launch the rocket up and you have it drop on the target from above. And it's fascinating, to me anyway, that that didn't even occur to us, right? We were just like, I just want to hit this weird dinosaur thingy with a cannonball. And the algebra told you, well, hold on, you have to make a decision. Are you wanting to hit the thing straight on to knock it backwards? Or do you want to hit it from above to knock it into the ground? And I guess that depends on the mechanism of your monster here. If you feel like crushing it into the earth is more effective than knocking it over, then you would choose the high solution. If you think knocking it over is more valuable than trying to crush it into the earth, then you choose the low one. Or if you're not really sure, then you get two cannons, you launch one at each, then you hit it twice from two different directions and really confuse it. Oh, what are we doing? Goodness, that was a lot of work. You notice I have some numbers here. One of them is the max height. And just from this calculation and the drawing, I've got two max heights. So I'm going to have to calculate this twice. Once for this angle, once for that angle. And to be honest, I really don't want to do that. Second thing, for time, I'd have to calculate these times differently. If you imagine this ball going this way, that's much faster than this is. It's quite a time lag that way. So to complete this chart, you would have to put 30.29 into here, here, and here. Calculate your max height, time, and time. And then you'd have to rinse and repeat, put 59.71 here, here, and here, and repeat the calculations. So I'll leave that for you to do as an exercise before you launch into the practice problems.